Welcome to Unit 9 and 10. This is pretty short. I know we have an exam. I will also say very quickly something about the review, but of course we will have a large review tomorrow. The first Unit 9 is about partial differential equations. Very exciting topic because this is the fabric we are made of. Partial differential equations describe laws of nature, finance, essentially anything you're doing are described by partial differential equations. And then we look at linearization, which is also considered one of the most important parts of multivariable calculus and calculus in general. The idea that we can look at something near a point, something linear near a point. Cool. So let's get started with partial derivatives. I don't think I have to say a lot. I've never met in 35 years of teaching, I've never met somebody who doesn't get partial derivatives immediately. What you do is you differentiate functions of several variables with respect to one variable, and the other variables are kept constant. The only thing you have to know is that the notation. And then we can also take mixed derivatives. We can also take higher derivatives like fxx or mixed derivative fxy. And then there is a beautiful theorem called the Clairaut theorem, which is the partial differential equation. It's an equation which involves derivatives with respect to at least two variables. And it's an equation. So what you have to know, and we will talk more in detail in class, are 5 differential equations. You have to know them, you have to recognize them. First of all, you have the transport equation, you have the heat equation, then we have the wave equation, the Burger's equation, and then the Laplace equation. The transport equation tells you if the slope fx is positive, then the function is increasing. So here the function will go up, and here, because it's negative, it will go down. So what will happen is that a bump like this will travel, and it will produce something like a transport. This is already more complicated. This is what we see here is actually a wave equation. That's this equation ft is equal to fxx. Let me just see whether I can capture. It looks like a pretty complicated motion, but you can actually describe this using Fourier analysis. We are not doing that in this course. We are just exposing you to a couple of partial differential equations. Heat equation also. The heat equation describes the propagation of heat. And when I make this hot here, I don't make it very hot here, just a little bit heated up. So what happens if I'm touching this here? It's very hot here. Now it starts to be hot here. Now it's about here hot. I can still touch it here, but it's getting hotter and hotter. Will diffuse and go to the rest. In the end, we'll have the temperature everywhere constant. So it's now already warm on the outside. So for the Burger's equation, this is an equation you see on the beach, and when you see waves coming, and then they are traveling. This is an example of an equation which is nonlinear. So this has a f and fx. So it's a transport equation where the waves which are higher up travel faster. And finally, we have the Laplace equation, which describes, which is used, for example, for a drum, describing a drum here. So usually here we have t and x as variables. T is time, and x is space. And in this case, we have actually both space, and this is an equilibrium. This is what we call a harmonic function. Now, there are lots and lots more of differential equations. So there's the Schrödinger equation, which is in quantum mechanics. So there's an I coming in here, which is it's like the heat equation, but there's an I coming here, which changes the nature of the thing. This is actually more like a wave. Then the Eikenall equation, that's something you see in optics. This is we will see this is actually the length of the gradient. We'll talk about the gradient just in a second. This is an exciting equation, Black-Scholes. It's an infamous equation in finance. Klein-Gordon equation, Sine-Gordon equation, Monge-Ampere's equation, Quadratic-Riesz equation, Euler-Tricomi equation. So these are Navier-Stokes equation. These are all equations which are somehow in physics or field theories are important. But you see they are relatively simple, but they have enormous structure. Some of them show solitons, like waves which interact nicely with each other. So also this is not linear because we have a ffx like here. And then we have a fxxx, which is pretty cool. Why does this fxxx really change things so much? So partial differential equations are also used to describe motions which are maybe more, discrete, like sand pile models. This is a standard camera. It's not one of these fancy slow motion cameras, which are which have thousands of frames per second. Now, I should also mention the Java lamp here. Okay, so for unit 10, linearization, this is something you know already in single variable calculus. So when we have a function of one variable, what we have is we write f of x with a function f of x, and then we define L of x is f of x naught plus f prime x naught times x minus x naught. So that's something I assume you know from single variable calculus. And what we do in 2 and 3 dimensions is exactly the same. So we are using the same idea. For the review, we will have a slideshow tomorrow. Look at the practice exams, it's the most important thing. We will also do a mind map, like a distance formulas, all the possible distance formulas, all the possible products, all the possible facts about curves, like integration, differentiation, and then look at geometric objects like